In this video, we'll be talking about some useful functions to memorize the shapes of. These are called parent functions. Now, we have seen through using different equations to graph several different examples of parent functions already. Every function can be written as a combination of parent functions in an algebraic sense. This works to our favor, especially in graphing. Namely, for example, we already know that the graph of a linear equation has the form f of x equals ax plus b. For that, see video 1.3.1, where here our slope m is equal to a and y equals b is our y-intercept. But we can really think of this as a transformation of the identity function f of x equals x with a scaling by a and then a vertical shift by b. We're going to talk a little bit more about this, actually a lot more about this in section 1 in the 1.7 sections. But for now, this is called the identity function because essentially whatever you plug in for x, it just gives it back. So it identifies the number, whatever you plugged into f of x. So now let's start by looking at some parent functions. So for our first example, the identity function, as we just saw, is the function f of x equals x. Now, what does this function look like? Well, the function f of x equals x is, if I pick 1, it gives me back 1. If I pick 2, it gives me back 2. If I plug in 0, it gives me back 0. Basically, whatever I plug in, it just gives me back. So -1 would be -1, -2 would be -2, -3 would be -3. And so I can plot these points, and so I just get the line, not surprisingly, of slope 1 with y-intercept y equals 0. Okay. Well, what's the domain? Well, we've seen the domain. We can look at this function and see immediately its domain is -infinity to infinity. Its only intercept is 0, 0. And its range is -infinity to infinity, looking at all the y values that get hit. It's increasing always, so -infinity to infinity. It's never decreasing, and it's never constant. Okay? We're going to go through and look at all these different functions and several different functions and do this for each one. So moving on, a constant function is any function of the form f of x equals c, where c is any constant real number. Here, so what does this look like? Well, this looks exactly just like, so f of x, no matter what we plug in for x, we just get the value c back. So whatever our c is, this will just create a horizontal line through that value. Well, then we see the only intercept will be 0, c. We also see our domain will be all real numbers. But our range is only going to be that value c, so just y equals c. Increasing, it's never going to be increasing. It's never going to be decreasing either because it's always constant. Okay. For our third example, we say the squaring function is the function f of x equals x squared because it squares whatever you put in. Namely, if we were to graph this, we would see that whatever we plug in, we square. So for instance, 0 plugged in would give us 0. 1 plugged in would give us 1. 2 plugged in would give us 4. 1, 2, 3, 4. And 3 plugged in would give us 9. So 4, 5, 6, 7, 8, 9. Okay. Of course, we've seen already that this is symmetric with respect to the y-axis. But this also happens, another way to think about it is because if you plug a negative in, squaring it gives you the positive value. So So it looks like just a standard parabola. Now, the intercept is going to be, the only intercept is at 0, 0. Its domain is negative infinity to infinity. Its range starts at 0 and goes all the way up to infinity. And it's never constant. It's increasing on 0 to infinity. So from 0 to infinity, it's increasing, but it's decreasing through here, which would be negative infinity to 0. On to our next example, the cubic function has the form f of x equals x cubed. What does that look like? Well, whatever you plug in, it cubes. It's important to remember, so first, if we plug a 0 and we get 0, 1 cubed is 1, but 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. Hey, look at that. Now, an important thing to remember is that this function actually has origin symmetry. This basically comes about because of the fact that if you take a negative number times a negative number times another negative number, you always get a negative number. And so we would have origin symmetry. Like so. So this is f of x equals x cubed as its graph. Its only intercept, as we can see, is 0, 0. Its domain is negative infinity to infinity, and its range is also negative infinity to infinity because of the preservation of the negative values. It is increasing always, which means, of course, it's never decreasing and never constant. And now we're going to go ahead and look at some more exotic sort of functions. So the square root function has the form f of x equals square root of x. Now here it's helpful to pick perfect squares. So 0, for instance, square root of 0 is 0. Square root of 1 is 1. But the next perfect square would be 4, because that's 2 squared. So we know the square root of 4 is 2. And then the next perfect square would be 9. So 4, 5, 6, 7, 8, 9. Square root of 9 is 3. Connecting the values, we have this. Now, the intercepts, and of course we can't do anything else because square root of negative numbers are undefined. But our intercept, our only intercept, it appears as 0, 0. It's increasing always, which means it's never decreasing, never constant. Its domain is 0 to infinity, and its range is also 0 to infinity. Moving on to the next example, the reciprocal function has the form f of x equals 1 over x. Now, what does that look like? Well, this one's a little bit weird because what it does is you take a fraction, 1 over it, flips it. So here, if we plug in 0, of course that's going to be undefined. But if we put 1 in, we get 1 over 1 is 1. Here we have, then if we plug in 2, we actually get 1/2. If we plug in 3, we get 1/3, which is about there, and at 4, we get 1/4. So it looks like it's just decreasing and getting closer and closer to 0 as we go out. On the other hand, though, if we look up here on this part, it's helpful to see here. So if we were to pick 1/2, it would flip that and give us 2. If we picked 1/3, it would give 1/3, it'd give us 3. If we picked 1/4, it would give us 4. So there's a nice, weird sort of symmetry to this. Okay. But it's also symmetric about the origin, because if you plug in a negative here, a negative in for here, it preserves it. So essentially, what that tells us is we can use that symmetry to help us graph it. go. Now, this function is interesting because it has no intercepts. Its domain is everything except 0. So in interval notation, that would be negative infinity to 0, union 0 to infinity. Just skip over 0. And its range is the same, because it goes up through here. You get up all these y values, then you skip over 0 and keep going. It's never constant. We're noticing a trend. And it's never increasing. It's always decreasing. Of course, that's only when it's actually on its domain that it can increase. Okay. All right, and now our last example, which is the absolute value function, which has the form f of x equals absolute value of x. Here, what does this do? Well, if you plug in 0, you get 0. If you plug in 1, you get 1, 2, 3, etc., right? On the other hand, though, if you plug in negative values, it takes the positive version. So negative 1 becomes 1, negative 2 becomes 2, negative 3 becomes 3. Or we could have noted that it has y-axis symmetry. Its only intercept is 0, 0. Its domain is all real numbers. But much like x squared, its range is only everything greater than or equal to 0. It's increasing from 0 to infinity, and it's decreasing on negative infinity to 0. And it's never constant. Now, the nice thing about, if you know these 7 graphs, you'll be able to go a lot further with what we're going to be talking about in the next couple of sections, or few sections, I guess. But it is important to memorize all of them. So again, this is what f of x equals x looks like. The identity function, this is what a constant function looks like. It's a horizontal line. The squaring function is this. The cubic function is that. The square root function is that. And the reciprocal function is that. And of course, the absolute value function is this. If you'd like to get some practice in identifying these functions, be sure to see the textbook, page 65, and work problems 2 through 10. In our next video, we'll be talking about how to shift these functions to get new functions.